Hi class, as I promised you previously, I'm going to give extra recorded sessions on applications of diagonalization. One of it here is a matrix representations of conic sections. Okay, so you will be able to calculate conic sections, axes, vertices, tangents, and poles, polar between points, lines of the plane determined by the conic. The example of conic over here can be a circle, parabola, ellipses, and many more. Now next, let's consider the conic equation given by equation 1 here. So 5x squared minus 4xy plus 2x squared y squared equals to 30. You can write this in terms of a matrix for which is the following. Okay, so you have a row vector of x and y, then a matrix M. Notice that a matrix M here we've previously solved for their eigenvalue equation, and you multiply back with the column vector of x, y that give you 30. Do note that the M is symmetric, and you can diagonalize M. Okay, then you find the diagonal matrix D, and they are connected by similarity transformation. Okay, and you can write this diagonal matrix in two ways, either 1 or 2. It's just you replace or interchange the order of the eigenvalue. Then finally, you can get the example of the conic relative to principal axis, right? So principal axis is after you rotate it, right? And then it's written as, so you have the new prime coordinate, you multiply with the diagonal matrix, and you have the column vector of the prime coordinate, make it equal to 30. As in the general equations of conic relative to principal axis, it's given by this red thing. Okay, so you see that your C minus 1 MC, your C is actually the unit vector, your eigenvectors, after you solve the eigenvalue equation. So if you just expand, okay, from equation 2 here, alright, and you notice that you get the equations of conic the after you rotate it, alright, subject to the principal axis. Okay, so if you choose a similar type of the order of your eigenvalue equations like this, then the equations will just change accordingly. Okay, so they have two ways of write down the equations of conic relative to principal axis. There's an interesting part that you can also find the angles, okay, that rotate your from x to prime. Okay, so it's given by the following. So previously you noticed that your eigenvectors matrices is actually equivalent to your rotation matrix C. Okay, they are equal, given by cos theta minus sin theta, cos theta, and your theta over there is actually the rotation angle, right? So in a schematic diagram, if you sketch them properly, you can draw, okay, you can properly identify V1 correspond, this the eigenvectors correspond to the first eigenvalue. Over here I choose eigenvalue 1 is 1 and the eigenvalue 2 is 6. You can also have eigenvalue 1 is 6, and then you have, or similarly you have eigenvalue 1 V1, or you can have eigenvalue 2 V2. Okay, they are interchangeable, but you are interested in this the angles of rotation. So if you want to compute the angle of rotation, so looking at the one that I have here, alright, so you find your cos theta is actually given by your x1 over the hypotenuse. Okay, so this is none other than, so you're taking your x1. What is your x1 in this case? Okay, so this is your, so I have now, this is my L2, L1, okay, which is equals to 1, which is equals to 6. So your cos theta here is your x1 is 1 over square root 5, and you divide by, because it's a unit vector, 1, then you get this part. Alright, This example is in 2D system, but definitely you can extend to 3D problem. Okay, so you can write, for example, here, rotate to principal axis the quadratic surface. Okay, you are given an equation 3 here. Okay, so you have more. Okay, and then you can rewrite them in a matrix form. Okay, so if you expand equation 4 here, you can verify that it's indeed similar to the quadratic surface. Okay, and then you can follow the same process such that now you have 3 variable. All right, 3 variable. So you're rotating to the subject to the principal axis of 3 variable now, so it's a surface. Then you still have these eigenvectors, eigenvalue equations to be solved, finding eigenvalue and finding eigenvectors. Remember, it must be a unit vectors, and then you can find the diagonal matrix. So in this case, the diagonal matrix is written in form of 1 0 0 0 minus 4 0 0 0 3. Okay, only on the diagonal term. All right. So each of these metric eigenvalue, all right, you can find their associated eigenvectors. Okay, so when you're writing down C and you compare to the rotation matrix in 3D, all right, and then you can get the but in 3D, what is the rotation matrix in 3D? All right, so in 3D, let me remind you again, the rotation matrix is just, let me, all right, so one of the rotation matrix would be, so you can have rotation matrix in 3D given by cos theta 0, okay, so you can try to plot, okay, or sketch, okay, sketch the eigenvectors, then you will be able to find data. Okay, all right, class, for the next part on the another example, characteristic using matrix to solve some more practical physics problems, I will give you in another sessions. Okay, thank you.